Hi, everyone. So my name is Barbara Chima. I'm professor at the University of Waterloo and also the president of the Canadian Mathematical Society. And it's such an honor to chair this session as part of this amazing program that's brought top mathematicians from around the world to gather here at Fields Institute. So of course, our program is forward from the Fields Medal. And one way of going forward from the Fields Medal is, of course, the Abacus Medal for Information Sciences, and that was previously known as the Nevanila Prize. And we've had one Abacus Medal speaker just earlier, and now our next speaker, Madhu Sudan, has won the Nevanila Prize in 2002. Of course, he started with his bachelor's degree in computer science at IIT Delhi in 1987, his PhD in CS at UC Berkeley in 1992. He spent time at IBM Research, MIT, Microsoft Research, and he's currently the Gordon McKay Professor in the John A. Paulson School of Engineering and Applied Sciences at Harvard University. Today, he's going to talk to us about algebra and algorithmic coding theory.
Great. Thanks, Barbara. Thank you all for coming here, and thanks to the organizers for putting up this wonderful event. And I think it is really nice that we are looking forward from the Fields Medal. On the other hand, I was looking at this talk today and contrasting it with what Maria said about her talk, she said she's talking about the stuff that she's been doing for the last 5 years. And I'm going to be talking about stuff that I have not done for the last 25 years. So maybe not so forward looking, but still hopefully something interesting. This talk is mostly designed for an average mathematician who may be interested in seeing how does math enter theoretical computer science. Mark's talk earlier told us about the kinds of questions that are raised by theoretical computer science and really home-built tools for solving them. In our case, we're more like importing tools from classical, very elementary, but classical algebra. All right, so I'll start by telling you about the basic problem of coding theory. Probably many of you have heard of this. If not, at least it'll put us on the same page. And then tell you about a classical algebraic object called the Reed-Solomon code, what it is, how it works, and also how it not only solves some very elementary algebra, not only solves a very interesting combinatorial question, but also leads to some very nice algorithmic progress over there. So this will be parts 2 and 3. And finally, I'll talk a little bit about, okay, not my own work, so I'm not cheating, but it is relatively recent work that's been going on over the last decade or so, maybe a decade and a half, which is taking us to the state of the art with respect to one particular question that I'll talk about later. All right, so what's the basic problem? This is a problem that dates back to the time of Shannon and Hamming from 1948, 1950s. And it's, with the advent of the digital era, we suddenly had the ability to communicate bits of information rather than continuous analog signals. But then it was soon realized that, of course, if you want to communicate bits, you have to do them very reliably because there can be a cascading effect, and small misinterpretations, small errors can lead to dramatically different implications. So this is an example sentence where one simple letter switch has completely changed the meaning of the sentence, and now downstream it could have major bad effects if it's not caught and corrected immediately. So in order to correct such errors, Shannon proposed this architecture. It's quite a remarkable architecture. He put in these two objects called an encoder and a decoder. Today, we would think of them as two computers, one which starts with some message that you want to send, but then expands it to something much larger, has lots of redundancy in it. It's an encoding function which maps k bits to n bits, or more generally from some big alphabet. For an example today, running example today would be a finite field over some large number of symbols, and expands it. So k will be some relatively small number, n will be much larger, and this is making the message that you're transmitting redundant. Your channel of transmission takes these elements of your alphabet, be bits or finite field elements, whatever it is, and sends them over, but it doesn't send them over faithfully. It sort of flips a few of these things. And the decoder now comes in and says, okay, let's take this long sequence with some few symbols which are incorrect, and then squish it out back to the k-bit sequence, a k-element sequence, and try to get the original message back. And that's the hope of this encoder and decoder together. And Shannon not only proposed this architecture, I mean, this architecture is quite remarkable for 1948 because there were no general purpose computers. And one might have, as was done by other mathematicians of the time, worked with very elementary functions, and for encoding and decoding, you can only add symbols mod in FQ or subtract them or something like that. But Shan said, oh, let's just consider the most generic function, whatever functions you want to consider the space of all such functions and work with them, and prove that there exist encoders and accompanying decoders whose ratio of, how much error do they want to tolerate. You decide that, you want to correct some epsilon fraction of errors. Well, in order to do that, you only need to expand the message by a constant factor. Okay, so if you fix the fraction of errors that you want to deal with, then you expand the amount of, and that error factor has to be sort of not 100%. It should be something bounded away from 100%. But as long as the fraction of errors is moderately small, in the version of the theorem that I'm describing, I'm just saying some constant fraction of errors can be dealt with some constant fraction blow up. This might, I mean, today many of us are just used to this so much that we don't consider this to be a sort of a dramatic statement. In those days, it must have been very, very puzzling, because in those days, people really thought the only way to make information redundant might be to resend the same message again and again. But if you're resending messages and I have k bits that I want to send to you, and I want to make sure all the k bits are recovered correctly, then you probably have to repeat every bit some logarithmic in k times, and then you're not getting a constant factor blow up. K bits get mapped to n equal to k log k. So compared to the wisdom of the time, this was already a remarkable statement. It uses general purpose encoders and decoders which are completely not available in the time, and but sort of sets the stage for future work. And the future generations basically were challenged with this question. Okay, this encoders and decoders are not explicit. We don't know which functions will work. We know that they exist, but how did we actually build one with an explicit one? And by the way, I mean, in Shannon's version, the functions need not even be succinctly described. In order to describe the function, I probably have to write a table of what the encoder does on every possible input and use that. Is there some way of representing them succinctly? That's called explicit functions maybe for us. And furthermore, can you make this algorithmically efficient? Make the encoding algorithm run in polynomial time and the decoding algorithm run in polynomial time. Coming up with encoders that run in polynomial time may seem plausible, and I'll show you an example of a code where it is. Decoder running in polynomial time would have been very surprising at the time, but actually even already by 1960, we'd managed to get some very surprising results. And let me tell you a little bit about those. So the Reed-Solomon codes, I mean, by the way, this is by no means an exhaustive description of error correcting codes and what can be done with them. I'm going to take a very minor path in this whole field, but the hope is I can actually give you proofs which are all understandable. The simplest example and the most beautiful example and a very, very, very powerful example of an error correcting code is the Reed-Solomon code. And the code has actually a very simple description. So for the time being, imagine I'm sending bytes, so numbers between 0 and 255. And I want to send 4 of these bytes. Maybe my message is, these 4 bytes, 100, 23, 45, and 76. This is the information that I want to send you. The natural way to send it over a channel that transmits bytes would be I send 100, 23, 45, and 76. But if it's going to flip 1 out of 4 symbols, then one of these 4 symbols could be wrong, and now you don't have the message available. So what do we do? The Reed-Solomon code, what does it do? This is a code from, I think, 1958 or 59 or 60. I don't remember exactly. So what does this code do? It says, let's consider a abstract object, a degree 3 polynomial, which is 100 plus 23x plus 45x squared plus 76x cubed. And I will send you this polynomial instead. But what does it mean to send a polynomial? I mean, I don't have a channel which transmits polynomials. It transmits bytes. So one way to send it is I can send the coefficients of the polynomials, but we just agreed that that's not a great idea. I don't want to send you a polynomial by sending its coefficients, because one of the coefficients could get flipped. Instead, what will I do? I will evaluate the polynomial at a few predetermined set of places and send you these values. So this polynomial p of x evaluated at 1 happens to be blah. Evaluated at 2 happens to be blah. 3, 4, 5, 6, 7, 8, 9, 10. Now notice that already when I send you the first 4 evaluations of this polynomial, you have enough information to recover the polynomial. I mean, a degree 4 polynomial can be recovered from its value at 4 places. Degree 3 polynomial from 4 places. But now I have the option of redundancy. I can evaluate it at a 5th point, a 6th point, 7th point, and an 8th point, and this gives me redundancy. And that is the redundancy that's sufficient to build an error correcting code. Let's see that this is a pretty interesting error correcting code. Suppose I evaluate it at this polynomial, by the way, could have had, it's always going to be in one variable, but it could have degree greater than 3. That allows me to send any sequence of k symbols. And I will evaluate it at n places. I need to be able to find n different points in my space, so my finite field has to have at least n elements. So if I'm working with bytes as my alphabet, the largest n can be is 256, okay? So I can find 256 points in a field of size 256, but there's no 257th point where I can evaluate. So I'm restricted, but these restrictions are easy to overcome. We won't worry about that today. For the time being, we're very happy with this alphabet being large. I'm going to be able to send bytes and at most 256 of them. And I can send messages which are much less than 256 bytes. So maybe I'm sending you k is 50, and I'm sending you evaluations of a degree 50 polynomial, 255 places. That's a lot of redundancy, should be able to correct a lot of errors. Does it correct errors? Well, we can see some already hints of this. Suppose the errors are very benign. Some symbols that I sent are transmitted faithfully. Others are erased, in the sense you see a thing saying question mark, this symbol was not received. Okay, first symbol not received, second symbol not received, third symbol is 75, fourth symbol not received, fifth symbol 77, etc. How many symbols do I need to actually receive in order to recover the original thing? Well, still just determined by the number of coefficients. So any subset of n minus k symbols can be erased, and I can still recover the original message. So this is a very interesting error correcting code. Using only this property, you can also prove that the following statement is true. If I have a so n minus k erasures can be dealt with equally, but I can also do the following. I can take n minus k over 2 symbols and actually change them to arbitrary other values. And now you receive what I sent you. N minus k over 2 of these symbols have been changed arbitrarily, and you don't know where they are, but but you're given a promise that that's the maximum number of symbols that have been changed. And now you can ask, do I have the information necessary to recover the original sequence? And here we can use the following very nice fact. So here is one polynomial, here is maybe another polynomial, and what I've written are all its evaluations, a sequence of evaluations. This is p of 1 here, p of 2 here, etc., q of 1 here, q of 2 here, etc. Now, how many places can the two of these polynomials agree? Well, there are going to be k places maybe where they agree. The rest of the places they're probably going to disagree. Now, no matter what sequence I write down here, I cannot agree with both of these polynomials on more than n minus k over 2 places, right? Because if I agree with both of them, sorry, n plus, I cannot disagree with both of them on less than n minus k over 2 places, because on each one of these points, I can agree with at most one of these two polynomials. And I have to choose which one of these I have to agree with. Once I've decided that's it, if this is what I received, this sequence is going to be within a distance of n minus k over 2 from either p or q, but not both. So this proves to us that with n minus k over 2 errors, we can actually recover the original information. This is information theoretic recovery, but this is not necessarily computationally efficient recovery. Okay, that's what has been proved so far. Question is, can you actually do this algorithmically efficiently? And indeed, Peterson gave us this algorithm in 1960, which does solve this problem. That solution is, I finally understand it and can claim unambiguously that it was more complicated than what we are going to describe today. But yes, it was a polynomial time algorithm and it works. Okay, so 1960, before the advent of the definition of P, we had polynomial time algorithms for solving this problem, which otherwise looks like a brute force search. Where can the errors be? That looks like a brute force search. What could the message be? That's another brute force search. All right, so n minus k over 2 errors, was this the limit? I will give you the algorithm, just hold on for a minute, but I'll actually give you an algorithm for a more complicated problem, which actually turns out to be, in some senses, even simpler to describe. So why was n minus k over 2 the limit for the number of errors? Well, I mean, we can just go back to this example that we just had. You know, we had a polynomial over here. I can take some polynomial called p. I can take some polynomial called q. I don't care how much they agree or disagree. I can just write down some received vector r, which equals p in the top half and equals q in the bottom half. Okay. Now, if I say correct n over 2 errors in this, how would you correct n over 2 errors if r is the received sequence? Okay. And by the way, today we are going to be talking of adversarial errors, malicious errors, errors introduced by, we're making no assumptions about the nature of the errors over here. Just the number of errors is all we are bounding. Now, if there are n over 2 errors, you can't correct them. That was the reigning wisdom at the time. If you actually do this analysis a bit more carefully, take your polynomials p and q so that they actually agree on some places, then you can even squish this down to n minus k over 2 errors is the maximum you can deal with. But that turns out to be not an inherent bottleneck. Why? In what sense? Well, if I receive this received vector r over here, and if I had an algorithm which said, oh look, the answer is either p or q, that is some meaningful notion of recovery, right? I mean, it's not like you're left at sea trying to figure out what the information was. You have two concrete pieces of things saying message was either this or that. Either this is the pictures of your grandchildren or this one is. And you know, you should probably know which one of these is your grandchildren. Well, not some of you who may not have any. So the n over 2 is, I mean, n over 2 is a limit only if you insist on unique answers. If you allow for a small list of answers, maybe you can correct more. I didn't prove that you can. In this example, two possibilities seem to describe the solution, but maybe there were more, or how do we know that? It turns out, at least we can define a notion called list decoding, which just says output a small list. How small is small, we'll not really worry about it too much. For us, a list which is polynomially large in the length of the transmission is small. Okay. Later on, you can worry about making the list size constant and so on, but as far as an algorithmic challenge is concerned, if the list is polynomially small, you can hope to create a polynomial time algorithm which outputs all of these things. Okay, I think that's Avi's cough. I heard that. All right, so now we're going to talk about the decoding problem for Reed-Solomon codes, the list decoding problem. What is this problem? I want to say, okay, even if you've sort of not been paying attention for what I said, it's actually a very simple self-defined, self-contained problem, and we want to give you an algorithm for this problem. Okay, so what are the problem described by? There is, maybe I should have said, okay, there's also a finite field. I described to you a field that I'm working over. We have a parameter n, which is the length of the transmission, k, which is the length of the message, and t is going to be the number of agreements. I won't be focusing on the number of errors, because I actually want to consider situations where the number of agreements is very, very small and errors is very, very large. And furthermore, we agreed on a sequence of places. I will evaluate the polynomial at points x1, x2, x3, and so on up to x sub n. But you already know x1 to xn. There is no ambiguity in the xi's. What's going to be unclear is what is the value of the polynomial p at x1, x2, x3. I'm going to send you p of x1, p of x2, p of x3 up to p of xn. What you receive is some sequence y1, y2, y3, and so on to yn. And what you know is p of xi often equals yi. Okay, so there's a lot of places where p of xi equals yi. Find me p. Okay. Is the problem statement clear? Find me p, find me all polynomials p which look like this. If the number of agreements is greater than n plus k over 2, this is like saying the number of errors is less than n minus k over 2, then the answer is unique, there was a solution. What I'm going to head towards today is a solution which says, well, we can actually find it as long as the number of agreements is square root of k times n. The AMGM inequality tells us that this is a smaller number than that, so we're making progress, in fact progress for all choices of k and n, but we won't get all the way there. We'll just give some ideas towards this kind of a solution. So the neat thing about this problem is you can actually draw pictures and look at it. So here is a picture. The finite field is no longer a finite field. I'm pretending this algorithm is going to work over the reals. It would work over the reals except for the issues that Lenore talked about. This is not going to actually, we will need an algorithm which actually deals with real numbers with infinite precision. And obviously, we're not going to have the ability to do that, but the pictures work. In this example, I'm looking at k equal to 1. What does k equal to 1 mean? The degree of the polynomial is 1. If degree is 1, that means you're looking for straight lines. I want straight lines which have t agreements, which means 5 agreements, where I have 14 points in the plane. So we were always given a bunch of points, xi, yi, and said, find me points which pass through the plane. So here, that's the Reed-Solomon question specialized to this instance. Okay, does this make sense? And presumably you've seen the solution already. Here are the two polynomials that we were actually seeking. Question is, how do you find this algorithmically, automatedly, mechanizably, without enumerating over all the lines in the space? I mean, enumerating over all the lines in the space is not very slow, but it's n to the k, and that's something that we don't want, or n to the k plus 1. We don't want that. We don't want to see the k in the exponent, so we want a solution which is kind of faster, different. Turns out that there is actually a very reasonable way to do this, and the idea is we're going to look for an algebraic explanation for all the points. Now, if I assume that this point over here is the origin, 0, 0, and if I assume that this radius is 1, then all the points lie either on the line x plus y equal to 0, or x minus y equal to 0, or x squared plus y squared minus 1 equal to 0, or the curve x squared plus y squared minus 1 equal to 0. Okay, so in particular, all the points satisfy this equality. Okay, and that's what we're going to try to find, this equation which explains all the points in the plane that are given to us. Well, I proved to you that these are all the points that satisfy this equality by noticing that the factorization by noticing that all the points lie on one of these 3 curves and then using multiplication. But the solution strategy, the algorithmic solution, is going to go through the steps in the reverse direction. It's going to start by finding this version of the polynomials and then apply an algorithmic idea to go to this explanation of the solutions. Why is the first one going to work? Well, the first one is okay. Let's go to the thing. Why was I able to find some low degree polynomial that worked in this case? In this example, it turns out I wanted to say, find me any degree 4 polynomial in x and y, which goes through all these 14 points. And it doesn't matter what these 14 points are, there is a degree 4 polynomial in x and y that satisfies them. Why? Count. You have 15 coefficients. There are 15 monomials of degree 4. And so you have 15 coefficients. And so there must be one polynomial which satisfies, it's not identically 0, but is evaluates to 0 in each one of these 14 points. There are 14 linear equations, homogeneous linear equations which work. More generally, if I give you n points in the plane, there is always a polynomial whose degree is at most square root of n in x, square root of n in y, which goes through all of these points. Okay. The definition of a polynomial in 2 variables going through point is q of xi yi equal to 0. So there is always such a polynomial because there are more than n coefficients, but there are only n constraints. And this is algebraically a much smaller degree than n, and that's where our gain is. Okay. We introduced an extra variable, got a huge reduction in the degree, and that's all we are going to count on. And once you have this explanation in the form of some degree 4 polynomial, we're going to factor it, and factorization, and this is the heavy hammer, is actually solvable in polynomial time. This dates back to work of Grigoriev, Kaltofen, and Lenstra, who solved this problem for bi and multivariate polynomials in general. Their algorithm in particular relies on work of, for example, Berlekamp, which solved this problem for univariate polynomials. So there was lots of history in the 80s solving these problems. And now we can just go through these 2 steps. Now the interesting thing is, well, we proved that there is a polynomial that fits all our points. Now, why is this why is this going to contain the lines? And it turns out that you can use Bezout's theorem in the plane to just say that, look, if there is a polynomial which goes through 5 of these points, a line which goes through 5 of these points, and I have this other degree 4 polynomial which goes through all 14 of those points, so in particular also through those 5 points, then this degree 4 polynomial and this line have 5 points of intersection, and that implies that the line must be a factor of this degree 4 polynomial. Okay, so this is just Bezout's theorem in the plane, and you just apply that as a black box and you can get this thing. And now now that you have this idea, you can basically say it doesn't matter what solution you found in this step, its factors will include x plus y and x minus y. That rest of it could have been anything else, and we don't know. Okay, so that's roughly how this algorithm works. It's a fairly simple algorithm. There's sort of more complicated things, but in the interest of time I will sort of skip it. But eventually you can get to algorithms based on this which actually correct n minus square root of kn errors. In particular, already in the examples that we've seen, corrects much more than 50% errors. Okay, and this is something that we didn't know how to do. Now you can not only do this, but it's also amongst, even if you want to correct n minus k over 2 fraction or less errors, this is perhaps the explanation that I would find. Okay. All right, so that's history. So this is roughly how the state was 25 years back. Since then, we've been looking at this question of, what can you do with these, so this seems to be a good way of correcting a lot of errors, but are we reaching the right limits? Are we reaching the capacity? So our code, recall, maps some k symbols to n symbols. The most number of errors you can hope to correct is n minus k. Okay, if I sort of simply erase the last n minus k symbols that were transmitted, that's a form of errors. I can replace them with zeros if you prefer, but you should really treat the zeros as erasures. You have only k bits, k symbols left. You cannot possibly, or if I correct n minus k plus 1, you have only k minus 1 symbols left. At this stage, you should have no hope of recovering the sequence. So n minus k errors is the maximum you should be able to correct. But can we actually get close to that limit? And it turns out this n minus square root of nk is not quite the limit. So I really want to be able to correct not from square root of nk non-errors. The capacity should be like more like k non-errors. So this should be non-errors. I should be able to correct from k, but maybe I'm willing to throw in an epsilon n extra non-errors. Maybe, okay, so let's get close to the right limits, but not do this. Can we do this? Are the Reed-Solomon codes capable of correcting this? And actually, it turns out this is a wide open question. We know that this actually question can depend on the choice of these points where I'm evaluating the x1, x2, x3, and so on to x sub n. If I choose it to be the whole field, then there's work by Swastik and others, which shows that there are some limits that you cannot quite achieve. On the other hand, the list size can be really large, is what they really show. On the other hand, there are other results which say that if these alpha 1 to alpha n are chosen at random from a large field, then with high probability this will work. But these are results which are very, very probabilistic and have no constructive elements. We don't know how to find the alpha 1 to alpha n. We definitely do not have algorithms for it. So this question remains open. So Reed-Solomon codes have not worked as far as getting to the right capacity is going. So question is there anything else? These are not the only codes in the world. Is there anything else that work? And this was, in 2006 in January, this was a wide open question. And 2006 in February, it was a completely closed question. So there was a dramatic result which actually led to this. And I'll tell you a little bit about these. These codes are actually not very different from Reed-Solomon codes. These are what are called folded Reed-Solomon codes. There's a fundamental theorem here, which is due to Guruswamy and Rudra, who showed they achieve capacity. And there have been sort of simplifications of the proofs. I don't know if I'll get to the proofs given the amount of time that I have, so I will I'll skip the rest of the references on the slides, but let me at least describe the codes to you and then maybe try to tell you a little bit about the decoding ideas. So the Reed-Solomon codes, recall your message was a polynomial and you just evaluated the polynomial at a bunch of places. Now I will evaluate it at a bunch of, let's say alpha is some primitive root of unity in this field. I'll evaluate it at alpha, alpha squared, alpha cubed, and so on in this particular order. This ordering was considered important for Reed-Solomon codes, but was completely unimportant. For the folded Reed-Solomon codes, it's going to have a meaning for us. We'll see it in a minute. So what are folded Reed-Solomon codes? Well, it's actually the same code word. It's just shipped in a new Ziploc bag. Okay, it's just a brand new packaging of this. I just take blocks of symbols of my original code word and call them single letters of the alphabet. Okay, this is a little bit of a play on definitions. From now on, when I'm counting an error, if any of these symbols is transmitted as an error, then the whole block is considered an error. Okay. Is this not cheating? No, absolutely not. This is the furthest away from cheating. If this is the kind of cheating you can do to get good results, you should, because we know how to go from here to binary codes which will correct very good amount of errors, or small alphabet codes which will correct up to capacity amount of errors. No, this is not cheating. This is completely legitimate in the game. You're allowed to choose your alphabet, and we will choose the alphabet, not to be a finite field, but a vector space over a finite field. Folded Reed-Solomon codes just do this, and it turns out now you're going to get capacity achieving codes. The only proof that we have that these are capacity achieving codes is algorithmic, by giving you an algorithm to show how to recover from the maximum number of errors. No other proof exists to show that this is actually going to achieve capacity, even though that's a purely list decodable, combinatorial statement. Now, an interesting aspect of the decoding algorithm is it works over this sequence of codes that I'll call a sliding window code. In a sliding window code, what I do is I take the same kind of an object, take the Reed-Solomon code, repackage its symbols, but now the symbols are going to be overlapping. Now the sliding window is a massive waste of utility, right? I mean, I'm taking this sequence now. Look at this sequence f of alpha cubed. It appears in the first transmitted alphabet, the second transmitted alphabet, the third transmitted alphabet. It's completely a bad code to use for any transmission purposes, but it's a great code to analyze. It's a great code to work with, and actually decoding algorithms work extremely nicely over the sliding window code. And one of the beautiful insights in this work of Guruswamy and Rudra was realizing that, oh, sliding window codes are not good for transmission, but they can be used in the analysis of folded Reed-Solomon codes. So recall, folded Reed-Solomon codes, disjoint blocks of windows, that's the alphabet. Sliding window, overlapping sequence. Why are these sliding window codes interesting and useful? Let me actually just skip to the theorem. If I take a sliding window where the window size is S, okay, so each one of these things contains S alphabets together, I can actually decode it from S times K plus N over S non-errors. Okay, think of S as a parameter that's going off to infinity. This is great news in terms of the epsilon n component. S is going off to infinity. The additive term is minimal and doesn't work. But this S times K is bad news. I mean, we really want 1 times K plus N over S. So this is bad. This is good. What can you do? Well, the insight is simple. I'll take some huge M and fold the Reed-Solomon codes with windows of size M non-overlapping windows. M is huge as a function of epsilon, but constant as a function of epsilon, right? Constant independent of n. Inside that, I'll see there's a huge number of sliding windows that are available to me. In fact, a block of length M contains M minus S blocks inside for free. And I'm recovering most alphabets of a size S, a sliding window code sitting over here. So when you put these two together, it turns out that actually I can take an MFRS code, just read inside it the symbols that I've actually been getting and say, oh, I've got lots of transmissions of an S sliding window code correctly. And now if I sort of translate the parameters and see what I get, I'm correcting from M over M minus S times K. That number is tending to 1 as S goes to infinity, provided M goes to infinity even faster. And this number is tending to 0 as S goes to infinity. That many errors I can get, and that's really of the form K plus epsilon n. And so this is how you get the thing. By the way, just sort of a brief picture of what the decoding algorithm looks like. It goes through the same paradigm as we have for, this is the decoding algorithm for the sliding window code. How do you get it? Satisfies more or less the same paradigm. Interpolate all the data that you have using some polynomial. The fact that you can now look at, you have sort of S-sized windows to work with allows you to work with S plus 1 variables, and this is great news because each variable you add reduces the degree of the solution. And so that's why we were able to get through with a lot fewer agreements that were necessary. And now, once you have this huge polynomial, you try to sort of analyze it algebraically. And polynomial which is explaining all the data, you analyze it algebraically, and then you can find the polynomial that you care for sitting somewhere inside. Okay, so summary is that algebra is giving us very powerful tools, and it was always well understood that there's combinatorial magic coming out of algebra over here, but I wanted to add the additional emphasis that there's also algorithmic power coming out of algebra over here. Things like factorization algorithms, the ability to find polynomials which satisfy a system of equations, and then to apply in your analysis tools like Bezout's theorem can be very powerful and useful. Okay. All right, thank you very much.